Welcome back to ECE 442-542. We are now going to present rules number 4 and 5 in sketching root locus diagrams. Rule number 4 is relative to how do we draw these construction asymptotes. These are helping us sketch the root locus by providing us with asymptotes or guidelines to show our root locus branches that are going off to these infinite zeros, the direction and the location where those need to be going branches wise. And rule number 5 is how do we depart from complex poles, or how do we arrive at complex zeros with these branches of our root locus. And we'll try to illustrate this with an example. And there are subsequent materials dealing with rule number 5 example wise. Now we are able, with these additional rules, to deal with many more poles and zeros than just ones, twos, or threes. We now can have a pole zero excess bigger than 2, and we can have these poles and zeros being complex. Here's the statement of rule number 4, and these are just asymptote lines. In some cases, the root locus branches will lie exactly on those asymptote lines, but in general, these are just guidelines that allow us to quickly sketch or see where these branches of our root locus that are going off to these zeros at infinity, where they are headed. Where are these branches going? The asymptote lines are guidelines for sketching the branches of the root locus that approach the zeros at infinity. That's the statement. Let's now develop some notation or define some notation. Let's let PZ sub E be our notation or variable for the pole zero excess. In this case, to the right, what is our pole zero excess? We have 3 poles, we have no finite zeros, and that's what we use number-wise to determine our pole zero excess. We have 3 minus 0, we have a pole zero excess of 3, or we actually have 3 zeros at infinity. So that's what this note says. The pole zero excess is really telling us, or another way of labeling the zeros at infinity. How do we determine that angle? And how do we determine where those asymptotes are centered on the real line? And that we will call sigma sub A. The angles we will call phi sub A. The asymptote angles, and here I hope you see that we have 3 such angles. We have an angle here, we have an angle here, and we have a third angle there. Those are our 3 asymptote angles, phi sub A, and those are indexed through this variable L that increments from 0 to 1 up to the pole zero excess minus 1. In this case, we have a pole zero excess of 3. We would look at L equal to 0, up to 1, up to 3 minus 1, or 2. So L would go through 0, 1, and 2 in this asymptote angle expression. We know PZ sub E is 3. We now have 180 divided by 3, or 60 degrees, scaled by 2L plus 1. When L is 0, phi sub A is 60 degrees. And again, these asymptote angles are subdividing our z-plane into uniform pieces. And here you can see that the z-plane gets split into 3 different pieces, each separated by an angle of 120 degrees. But in this case, our fundamental angle, phi sub A, the fundamental angle is when L is equal to 0. That's 60 degrees. The next one is 60 times 2 plus 1, or 3. That's 180 degrees. And finally, we have L equal to 2, We now have 5 times 60, or 300 degrees, which makes sense because that's now 60 degrees below 0, or 360 degrees. So in this case, when we had 3 poles, no finite zeros, we have asymptote angles of 60, 180, and 300. Where do those angles, or those asymptotes, where do they emanate from, or where is their centroid? Where are they centered on the real line? That's what we call sigma sub A. Sigma sub A is the centroid, and that is determined by taking the sum of the poles minus the sum of the zeros divided by the pole zero excess. In this case, we didn't have any zeros, so that second term in the numerator wouldn't even be present. Let's look at an example. Our fundamental asymptote angle, which I'm calling phi sub A, is going to be when L is equal to 0, and sigma sub A is the centroid for those asymptotes. This is then how we would create. We now know how to draw the root locus with those asymptote angles as guidelines, or those asymptote lines as guidelines. Which line segments belong to the root locus? We have that line segment that actually possesses 2 branches, and we have this line segment. This one of those goes to the right, this one goes to the left. We could calculate the breakaway point. One of those is going to go up here, the other one's going to go out there to approach those asymptotes. That's why they're called asymptotes. They are being approached by these branches, and one of the branches goes off to minus infinity. We have one going off at plus 60 degrees, another branch going off at minus 60 degrees. The center, the centroid for those asymptotes, we can calculate by just summing up. And in this case, we have this location, let's say that was at 1, those 2 poles are at 0. We now have 1 divided by the pole 0 excess, or 1 divided by 3. That centroid would be at 1/3. That's rule number 4, and that allows us to sketch root locus diagrams when we have a pole 0 excess bigger than 2. We now know where those branches are going to go, how they're going to move off towards those zeros at infinity. Rule number 5 is the direction that the root locus possesses near complex poles or complex zeros. We know the root locus branches start on the poles, so these angles are going to be our departing angles, or departure angles, from the poles. And we know that our branches terminate on finite zeros, so our arrival angles, alpha sub A, are going to be what we use to determine the angle of approach that our branch takes as it approaches those complex zeros. And all of those angles, alpha sub D and alpha sub A, can be determined from the phase angle condition. Here are a couple of examples. One on the left is for determining the departure angle. We're departing from the poles. And on the right, we're doing the arrival angles. How are these 2 root locus branches approaching those zeros? Notice that I now have indicated an arbitrary point, epsilon, very near, and this is an epsilon away from that pole in the first quadrant on the example on the left. If that is epsilon away from that pole, then I can fairly easily determine the angle theta sub P1. Now that angle to go from the pole in the fourth quadrant up to that point epsilon that is supposed to be on the root locus, that's going to be 90 degrees. The angle from the 0 at the origin to that point epsilon, which is very close to the pole, so it might as well be at the pole. I can now compute that angle, theta sub z. If I do that here, let's just sort of eyeball some of those angles in this scenario. And alpha sub d is the angle that takes me from this positive real line segment to a point on the root locus. That's the definition of alpha sub d. That needs to be my angle. All of these angles, any point on this root locus has to have an angle of minus 180 degrees. So if this point is on the root locus, then this angle minus this angle and this angle needs to sum to minus 180. That's why I can say, oh, an epsilon distance away from that pole is some point on the root locus. Theta sub z in this case is, let's just say that's 45 degrees. Theta sub p sub 1, that's 90 degrees. Now the only unknown in that expression is alpha sub d, which is the angle that the root locus is making with respect to that pole. So in this case, we have 45 minus 90 degrees. That's minus 45. We can add 45 to both sides and move things back and forth, and we actually see that alpha sub d is 135 degrees. And that's why I can confidently sketch that root locus going off at a 45 degree angle to the vertical, or at 135 degrees from this positive real line. The root locus diagram is symmetric, so that means that I'm leaving this bottom pole at an angle of minus 135. We do the same thing over for this example on the right. How many angles do I have? I now have 3 poles, so I have 3 angles, one for each of those poles. I have 2 complex zeros, and the angle that this, or that the root locus is making relative to this 0 in the second quadrant is what I'm calling alpha sub a. The angle theta sub z1, I hope you can see, is 90 degrees. Theta sub p1, that's going to be 140 degrees or something. The angle theta sub p sub 2 is now going to be maybe 135. Maybe theta sub p sub 2 is 120. All of those now need to be minus 180, equal to minus 180. The only unknown is the alpha sub a, the arrival angle, and we could then solve for that once we've computed the known angles theta z1, theta p1, theta p2, and theta p3. Let's talk a little bit more about the background behind rule number 4. Suppose now somebody gives you this pole 0 pattern, and we want to know, why can we claim that rule number 4 is a valid rule? Well, suppose we are a far distance from this configuration of pole 0 pattern. What does this pole 0 pattern look like if we are a long way away? And that's what's happening if we are at an infinite 0. We're a far distance from that pole 0 pattern. Well, a long way away, do you see that in the aggregate we have 3 poles and 1 0, so effectively from a far distance away that would look like 3 minus 1, or 2 poles. So now we say, oh, that's going to be approximated by 2 poles. These are not actually poles, these are just pseudo or sit-in poles. These are the aggregate poles that this pattern looks like when we are a far distance from that region that's close to the origin in the complex z-plane. We can now determine what these 2 poles, these aggregate poles, what their angle makes to a point a far distance from those aggregated poles and zeros. We actually can see that they are located at some point on the real line called sigma sub a, and we now have something that effectively looks like that transfer function. We could now say, oh, well, the angles of those two poles have to sum to minus 180 if in fact though that point, that red dot, belongs on the root locus. That's the definition of a root locus. So now we know that those two angles, theta p1 and theta p2, are the same. So we can just say, oh, we have two theta p1s. We're subtracting those because they're poles. They are in the denominator. Those sum to minus 180. We can now say that theta p1, we can multiply by minus 1 on both sides. That's actually equal to this asymptote angle, phi sub a, of the fundamental angle, and that's going to be 180 degrees divided by 2, or that's going to be 90 degrees. The general formula for finding sigma sub a, we just sort of did a hand-wavy discussion of how that might appear. In the aggregate, a far distance away, you can actually calculate that sigma sub a, the centroid of the root locus asymptotes, by taking the sum of the poles, subtracting from that the sum of the zeros, and dividing by the pole zero excess. And that sigma sub a, the centroid, is the point on the real line or the real axis where those asymptotes are centered. That's the definition of sigma sub a. The angle of those asymptotes, these are now the construction asymptotes that are drawn from that particular point, sigma sub a. We can now figure out what the angles are that they make with the real axis from that point. And that's now 2L plus 1 times 180 divided by the pole zero excess, and L now gets evaluated from 0 to 1 to 2 up to pz sub e, that's the pole zero excess, minus 1. Let's look at what that does for a specific example. Suppose now we have this plant, we have 3 poles, we have no finite zeros, so in this case our pole zero excess is 3. We can now immediately calculate the asymptote angles. Phi sub a is 2L plus 1 times 180 divided by the pole zero excess. The pole zero excess, or L now, is incremented from 0, 1, 2, up to, remember that's pz sub e minus 1. In this case, if pz sub e, the pole zero excess, is 3, we just need to work this out for L equals 0, 1, and 2. And if we do that, we see that we have 180 divided by 3 times 0 plus 1, that's 60 degrees. We have, when little l is equal to 1, we now have 3 scaling 180 divided by 3, or that becomes 180. And finally, we have 180 divided by 3 times 2 times 2 plus 1, or 5. Now we have effectively then 60, the fundamental angle, times 5, which is 300 degrees. Our asymptote angles are 60, 180, and 300, and those angles are centered at a point determined by the centroid. And the centroid is now the sum of the poles. We had a pole at minus 1/2, we have a pole at 3/4, and we have a pole at 1. We sum those, we have minus 1/2 plus 3/4 plus 1, no finite zeros, so that quantity is empty in the parentheses for our sum of 0 values, divided by the pole zero excess, which is 3. We now have 5/4 divided by 3, or 5/12, which is a little less than a half, or sigma sub a is 0.4166. That's now what this value is right here. There's sigma sub A. That's a little bit less than 1/2. We have our 3 poles. One pole was at minus 1/2. One pole was at 1, and the other pole was at 3/4. Those 3 x's, we now know which segments from rule 2 belong to the root locus on the real axis. We know we break away between the 2 rightmost poles, and we know that these angles, this is 60 degrees, this angle is 180 degrees, and this angle is 300 degrees. We typically just keep track of that fundamental angle, 60, and then realize that this z-plane gets subdivided into uniform regions. And in this case, they're wedges of 120 degrees in angle. Now we could flesh this out a little bit more with a little bit more detail by finding the breakaway point. What's the breakaway point in between 1 and 3/4? Well, that's just the value of k that's a relative maximum between that location. So the breakaway point we can determine from the magnitude condition. The magnitude condition says k times g. That magnitude equals 1, and we know that that's occurring somewhere on the real line between 3/4 and 1. We can solve that condition for k, and we now can plug in different values of z between 3/4 and 1 and look for the relative maximum. And we could do that with our calculator, we could do it with calculus, but we could do it numerically. We could just iterate a few points between 3/4 and 1 and look for where's the relative maximum. In this case, the relative maximum occurs at 0.881. Now what? Well, we now can find the value of k at that particular real axis point, and the value of k is now 0.011. So as we're adjusting this knob, it doesn't take much adjustment on k to get us to the breakaway point. So we're going from 0 up to 0.01, and at that point, that value of gain k, we have 2 real equal poles on the real line to the right of the origin. We have another pole to the left of minus 1/2, and it didn't take us very much gain increase to get us to that location before the poles started to break away. We can now try to figure out what's our upper bound on k for stability. We know where we're breaking away. We know we're probably stable at 0.011, but we need to verify that. Let's now look at the k value to push this third branch from minus 1/2 all the way over to minus 1 and see, is that bigger than 0.011? If it is, then our poles haven't yet left the unit circle when they're all 3 real. We calculate k from our formula at z equal to minus 1, and it's 0.875. So that's quite a bit bigger than 0.011. We can then figure out what is the gain k to get us to that triangle location, and now we're comparing that with this 0.875 that made us go outside the unit circle on the left. Well, we could eyeball that triangle from our sketch. We know that we've broken away at 0.881 for z sub b, and we know the branches are approaching those at construction lines, and that will now allow us to sort of more effectively determine where those points are that are indicated by triangles. Let's just say that they're at 0.9 plus j 0.43. We kind of eyeballed that. That now gives us a gain of 0.1472. That value is less than the 0.875, so in fact, we leave the unit circle with those two branches that are approaching those construction asymptotes much sooner than we leave the unit circle going out towards -1 or to minus infinity. So the point z sub delta of 0.9 plus j 0.43 is the value where we first find that we go unstable. Here is our closed loop configuration. We can compute our closed loop transfer function, kg over 1 plus kg. We've determined what we think to be the upper limit on our stability, which is 0.147. We can now find what our poles are for these different values. Here is our characteristic equation. That's the denominator of our closed loop transfer function. That's 1 plus 2g, or actually kg, and g, it was 2 over z plus 1/2, z minus 3/4, and z minus 1. Let's go ahead and evaluate that when k is equal to 0.1472, and in fact we end up with this 0.94 plus j 0.42, and in fact that value is now, when k is equal to 1.1. So now let's just go ahead and let k be 0.11. Are we stable? Well, what was our upper bound for stability? Our upper bound for stability was this 1.1, so indeed 0.11 is a stable upper limit. Suppose we said, oh, let's back off on that even more, and let's let k be the gain when we are just ready to break away from the real line between 3/4 and 1. And that will now give us 3 real poles. We could say then that that's at the breakaway point, which is 0.881. That's our dominant pole. That's the pole, and there's 2 at that location that are real and equal. We can determine what our settling time is going to be from that dominant pole. That's our r is 0.881. We can divide the log of that, base 10, into -2, and we see then that our system will settle in about 37 sample periods. That may or may not be adequate. If it's too slow, what did we start with? Here we just looked at a proportional controller, and that was k sub p. We could maybe introduce a PI controller, or if we step it up a notch, now we might try a PID controller, which now has more design flexibility. We have the pole at z equal to 1, that's the z minus 1 factor. We also have a very fast pole, a pole at the origin, that's the z, and then we have 2 zeros that we can select, so we have 3 parameters in a PID controller to manipulate. In the P, we have 1 parameter, that's the gain, that's what we just had in our example. Here in a PI controller we have 2 parameters, and in a PID we have 3 parameters. Our system then, if we controlled it with a PID controller, we could do something like the following. We could say, oh, we now have, or what would we do? Now we have to start asking many different questions as to how we might control that system and what that control might look like. Here we started with a system that looked like this. We had those 3 poles. Now if we actually tried to control this with a proportional controller, we found that we had that, and these two broke away and went off in that direction. If we introduced a PI controller forces a pole there, and it forces another pole. It gives rise to another 0, and that 0 maybe we could put there. But that now, look at what that does. This was z equal to 1, so these immediately are unstable. So the PI controller actually is going to immediately force us into an unstable situation. And now the PID controller, that puts a pole there, and if we just canceled that by the other 0, we're still in the condition that we had for the PI. So we may have to use more strategies than just a PID controller or a PI controller to achieve the necessary behavior that we want for specific question or for specific plants. And that's why we might want to look at more generic controllers beyond just PI, and PID controllers. But hopefully this now gives you a feel for how you might approach a problem for rule number 4. Rule number 5 is introduced in some subsequent videos. How do we depart complex poles, and how do we arrive on complex zeros?